This is Physics 30, Chapter 5, Lesson 2 on the conservation of momentum. Conservation of momentum basically means that the momentum before a collision will be equal to the momentum after a collision. Why science teachers should not be given playground duty? Because they may end up using the swing set as a Newton's cradle. Big fish versus little fish. The mass of the big fish is 4 times the mass of the little fish. If the smaller fish is moving initially at 5 kilometers an hour, then the combined speed of their collision together will be 1 kilometer an hour. We know that if the amount of mass in motion increases by a factor of 5, then the velocity will have to decrease by the same factor of 5 in order that the momentum before and after work out to be the same thing. We can see this with a simple calculation. We know that momentum is calculated P equals mv, where momentum is equal to mass times velocity. Now we don't know the specific masses of the fish. All we know is that the larger one is 4 times the mass of the smaller one. So for simplicity, let's just say that the small one has a mass of 1 kilogram and the larger one a mass of 4 kilograms. Then the momentum initially of the large fish would be a total momentum of 0 because its velocity is 0, it's just stationary. And the momentum of the smaller fish would be 5 because it's weighing 1 kilogram and it's moving at 5 kilometers an hour. So the overall total momentum before the collision is 5 plus 0. Now we know that that needs to be equal to the momentum after the collision. So we can use the same equation, P equals mv, where the momentum will be 5 because it has to be the same as it was before. The mass, once the smaller fish is swallowed, will be a total mass of 5 as well, the mass of the large fish plus the mass of the smaller fish. So we end up with 5 equals 5v, and then we can simply determine that the final velocity would be 1. So we can see that if the mass of the moving item from 1 kilogram goes up by a factor of 5 to 5 kilograms, then the velocity of 5 will reduce by the same factor to a velocity of 1. Consider now if the large fish was the one moving at 5 kilometers per hour. If the mass goes up by a factor of 5 over 4, then the velocity should decrease by a factor of 5 over 4. Now we're going to wait for this animation to start again, and when it does, notice that it's saying the initial velocity is 5 kilometers per hour right here, but it says here that the final velocity is also 5 kilometers an hour, which is actually a misprint. That's not possible. So using the equations that we just did before, see if you can pause the video here and calculate what that final velocity should actually have been, knowing that if your mass increases by 5 over 4, then the velocity should decrease by 5 over 4. So using this same situation, but now the larger fish moving at 5 kilometers per hour, it will have an initial momentum of 20, and the small fish will have an initial momentum of 0. Meaning overall our total momentum at the beginning is 20, and the total mass again will be 5, so the final velocity in this scenario should be 4. Another scenario. A 1,000 kilogram car is moving at 20 meters per second right, and it collides with a 3,000 kilogram truck moving left at 20 meters per second. Now, just thinking about this logically, because we can see that their initial velocities are identical. Because the truck weighs more, it has a larger mass, that means it's going to have more momentum, and therefore after the collision, things will continue in the direction of the truck, just because it has more initial momentum than the car does. We want to know if they stick together, how fast do the two vehicles move after the collision? So we can draw this as a free body diagram with the car in the green and the truck in yellow. We know eventually they're going to end up moving left, but we're not sure what that final velocity is. However, we do know when they stick together, the final mass will be 4,000 kilograms. So we know momentum before is equal to momentum after. So we end up with this equation. The mass and velocity of the car plus the mass and velocity of the truck. So this would be momentum of the car. This is momentum of the truck. That total momentum needs to be equal to the total final momentum, which would be, since they're stuck together, we can combine their masses and multiply that by the velocity. So plugging in everything we know that the car is 1,000 kilograms moving at 20 meters per second. The truck is 3,000 kilograms, and notice since it's moving contrary to the car, we have to put its velocity as a negative so that it counteracts the other velocity. And then their combined mass is going to be 4,000 kilograms, and we want to know that final velocity. Calculating it out, we get a final velocity of negative 10 meters per second, just meaning that we're ending up moving 10 meters per second to the left, which is what we were expecting. Consider now a 3,000 kilogram truck moving at 20 meters per second right, colliding with a 1,000 kilogram car that is sitting still. If they stick together, how fast do the two vehicles move after the collision? Again, free body diagram. We know the whole system after the collision will move right, so we can consider all of our velocities as positives. So we've got mass and velocity of the truck plus mass and velocity of the car will be equal to their combined masses multiplied by the final velocity. The truck is 3,000 kilograms moving at 20 meters per second. The car is 1,000 kilograms moving at 0 meters per second. Their final combined mass is 4,000 kilograms, and we're looking for the final velocity. Doing the calculations, we get that their final velocity will be 15 meters per second, and that's a positive, so it will be moving towards the right. For practice work, we're going to look at page 232, numbers 2 to 8.